Today, we are diving into the Golden Goose paper. It introduces a really clever method to get around a huge bottleneck in reinforcement learning with verifiable rewards, or what we call RLVR. And as you'll see, this has some pretty serious implications for how we scale up the reasoning abilities of large language models.
So, let's set the stage. We know RLVR is a cornerstone for training advanced reasoning in LLMs, but right now, progress is hitting a wall. There's a fundamental data problem that's basically stopping the next big leap in model performance.
The heart of the issue is data saturation. Models that we train on the existing verifiable data sets, well, they're showing diminishing returns. You can throw more compute at them, but after a certain point, you get no meaningful improvement. They just plateau, hard.
So why is this happening? Well, creating this verifiable RL data is just incredibly difficult. It's expensive, it's slow, and it needs domain experts to create and verify. And maybe the biggest problem of all is that it's stuck in these narrow fields like math and code, where you can programmatically check if an answer is right. This leaves out this massive treasure trove of text from things like textbooks and scientific articles, all because we can't easily verify the solutions.
And this is exactly where the paper's core innovation comes in. To get past this data wall, the authors came up with a completely new strategy, and they call it the Golden Goose method. Now, the solution here is pretty counterintuitive. Instead of trying to create more of that expensive human-verified data, the authors propose leveraging the huge, messy corpus of unverifiable text out there on the internet. The very resource we previously thought was useless for RLVR.
So what is the Golden Goose method at its core? It's a data synthesis pipeline. It's designed to take raw, unverifiable text from sources like a science textbook or just scrapes from the web and cleverly turn it into verifiable RL tasks. And the trick is how it frames the problem as a fill-in-the-middle task, packaged up as a multiple-choice question.
Okay, so here's how the pipeline actually works. It's an automated 5-step process. First, an LLM pulls out a passage that's educationally valuable. Then it finds a critical reasoning step in that passage and just masks it out. The text it removed, that becomes a ground truth answer. From there, the model generates a bunch of plausible but wrong answers, the distractors. And voila, you've got a verifiable multiple choice question where the only way to be right is to pick the original unmasked text.
A clever method is one thing, right? But the real question is always, does it actually work in practice? Well, the authors put this to a pretty rigorous empirical test.
And they didn't just dabble, they went big. Using this pipeline, they created a whole new data set called Goose Reason, and it's got over 700,000 RLVR tasks, all synthesized from things like university-level science textbooks.
And the utility of this data is, well, it's striking. Let's look at an already saturated model. For that model, only about 25% of the existing ProRL data was still effective, meaning the model still struggled with it. But in contrast, a whopping 70% of the new Goose Reason data was still challenging. That provides a really strong signal for continual reinforcement learning, showing a massive jump in data utility. So the first key experiment was to see if this new data could actually bring a plateaued model back to life. They took a strong open-source model that had already saturated on all the existing RLVR datasets and just kept the training going.
The results in mathematics are just definitive. You can see the control model, the purple line, continuing on the old ProRL dataset. It's completely flat, total plateau. But then you look at the green line, the model trained with Goose Reason data. It shows robust, sustained improvement. It completely smashes through that saturation point.
And this isn't a one-off. We see the exact same pattern in coding benchmarks. The ProRL dataset leads to stagnation, but once you introduce the Goose Reason data, you reignite that learning curve and push performance way beyond the old plateau. But the most dramatic impact really is in general STEM. The performance gap here is even wider, and that's because this is a domain that had the least amount of RLVR data to begin with. By synthesizing new tasks directly from science textbooks, Goose Reason filled that gap and delivered a huge 3.48 percentage point gain over the baseline.
Now, to really prove how versatile this method is, the researchers applied it to a completely new, highly specialized domain, cybersecurity. We're talking about an area with basically zero existing RLVR data.
This was a true stress test. They used the Golden Goose pipeline to create a brand new data set, Goose Reason Cyber, synthesizing it directly from unstructured web text. Then they took a 4 billion parameter model and trained it on this totally novel data.
The result was pretty incredible. The 4 billion parameter model, trained only on this synthesized data, set a new state-of-the-art on cybersecurity benchmarks. Get this, it actually surpassed a much larger 7 billion parameter model that had already been heavily fine-tuned for the domain.
So, what's the big picture here? What does all this really mean for the future of reinforcement learning? Well, this method really represents a major paradigm shift.
The main contribution of Golden Goose, when you boil it all down, is that it gives us a scalable, automated way to convert the entire internet, all that messy, reasoning-rich, unverifiable text, into high-quality training data for RLVR. It effectively solves the field's most critical data bottleneck.
And this all leads to a really provocative final question. If this synthesis method works for STEM and cybersecurity, could we apply it to other complex, high-value domains like law and medicine? You know, fields that have tons of professional literature, but almost no verifiable training data. The Golden Goose method suggests there's now a viable path forward for unlocking internet-scale reinforcement learning in just about any discipline you can think of.